Okay. So, tight binding model. So, we start with just one atom in isolation, in vacuum, with nothing around it. Here is my atom. So, the core actually of the atom, the positively charged core. Okay. And let's make things very, very simple. Let's keep, the physical situation very simple, because we have to grasp the idea. So we will consider an atom which has only one electron in the outermost orbit. It could be a sodium. Sodium is a good example. So 3s electron of sodium. Or you can even take hydrogen, which has just one electron, 1s electron, right? So we are dealing with a situation where the electron resides on the s orbital, just to keep things simpler, because it is spherically symmetric. Okay. If you take a p orbital, it will only make a little bit of change here or there, but the basic concept will not change. The basic idea of tight binding will not change, right? So we are assuming that we are dealing with an s orbital. So the electron, it sees a potential, and that potential that it sees can be drawn like this. This is 1 by r potential that the electron sees when it is orbiting around the nucleus, right? That's the potential it sees. So therefore, this electron, it satisfies the Schrodinger equation, which can be written as minus h bar square by 2m del 2, again 1d, just for simplicity. I mean, this atom has to be, I mean, we have already said it's spherically symmetric, but just to keep things simple. And then the potential, this potential, I will call this potential as v, little v, v of x. So this is 1 by x. And this is of course not 1 by x, this is some constant by x, 1 by 4 pi epsilon naught or whatever, right? So this is some, okay, lambda by x. So plus Vx, that's the Hamiltonian, okay, for this situation. And let's say the orbital that you get is phi naught. That's the wave function. And we will call it an orbital, just to be on the same page as the other books. And let's say E naught is the energy eigenvalue, like. Okay. So basically, you can then say that h phi naught is equal to E naught phi naught. Now, if I bring these atoms, as I said before, closer from infinity, out from infinity, bring them to the equilibrium separation, these 1s orbitals will start overlapping. The 1s orbitals of the adjacent atoms will start overlapping, right? So let's first show this pictorially. So here are the atoms, ionic cores. Let me draw how many? 1, 2, 3, 4, 5. I think 5 should be good enough. So, any guess how the potential will look like now? Well, I believe it wouldn't look any different from what we have drawn here, right? The fact is, it wouldn't look any different. The only difference would be that this potential is now more steep. It does something like this. So in fact, if you like, in the case of metals, though we have not yet shown that it's a metal or an insulator, but if this material happens to be a metal, then you can show. I didn't do it in this course, but I should. I mean, one should do it actually. That the potential will go as 1 by r, which it was actually originally, but then there will be a damping by an exponential factor, and this will be minus r by rtf, and this rtf is a distance at which the potential would have dropped by 1 by e of its value when the atom is in vacuum in isolation. This is known as Thomas Fermi wave distance or something like that. So this basically refers to the screening that happens in a metal, right? So basically the potential of an ion in a metal is screened. So beyond this distance, basically the potential is really very, very weak. You don't really see it. The electrons don't see it. But that's again a side information. We don't really know the exact form of this potential. So we are going to just call it as V of x. So what is V of x? V of x is sum of these little v's at various sites. And now I'm going to name these sites, lattice sites. This is my n equal to 0, n equal to +1, n equal to +2. What are these n's? These are the integers to index the Bravais lattice, the 1D Bravais lattice. R vector is equal to nx. These are my n's. So here is the atom at site -1, the atom at site -2, and so on. And what is the question we are asking? The question we are asking is, how are these going to change when you will bring the atom from infinity to a situation like this? So what are we going to do is, we have to find the solution to this problem. Now the Hamiltonian of the same electron in this situation would look like this, H equals minus h bar square by 2m, the kinetic energy, del 2 del x square. But this time you don't have a little v over there, you have a capital V over there. That's the difference. Same electron seeing this potential rather than this potential. Okay? Now, how am I going to solve this problem? Because it's a many body problem. So I have to again use some trick of the quantum mechanics. So I'm going to write this as 2m del 2 del x square plus Vx plus V prime x. What have I done? I have written Vx as a sum of these two. What are these? This is the atomic potential. So this is the atomic potential for the atom at the 0th site, let's say. And then this, what remains is this. V prime x is V x minus NA summation over n. That will be V. Now what is V prime? V prime will be all this except for the potential due to the atom at the 0th site. So same thing, summation over n, but n not equal to 0, excluding n equal to 0, V of x minus NA. So this is the potential of the atom the potential seen by the electron due to the atom at n equal to 0. Is this clear? Does it make sense? So can someone help me drawing v prime x? What will be the graph of v prime x? V prime x is this. We have drawn the graph of v of x. What will be v prime x? Let's try drawing it on the same. So the effect of this term Vx is only here, right? So we have subtracted this part. Elsewhere it's going to be the same, more or less. So it will be the same. Except here. So here it will become like this. So what I have drawn with yellow is v prime x. This is v prime x. This is v of x. Just uprooted, let's say one atom, then this is how the potential will look like. Okay. I should. They are nearly the same Vx and V prime except in the vicinity of x equal to 0, and this is how it has been modified. Okay. So now how should we solve this problem? Yeah. You have a question? Okay. So how should we solve this problem? I mean, now it's more of a problem, more of a like a lecture in quantum mechanics. We have to solve this problem. So what we are going to do is, we are going to we cannot treat this as perturbation because it's not weak. Had it been weak, we could have treated it perturbatively and used the same technique which we used yesterday, right? So here what we are going to do is, we are going to use another very commonly used method in quantum mechanics, variational principle. Do you remember using it before? Which problem do you remember? Where did you use it before? Did you do variational principle first of all? So which problem did you use it for? Hydrogen molecule, right? Hydrogen molecule ion, H2 minus. That's the problem, classical problem that you solve using the variational method, right? So if you have solved that problem, then what we are going to do now is very similar to the problem of hydrogen molecule. So what do we do in this method? We pick a trial wave function, right? And then what do? Then we compute. So let's say psi q and EQ. This is the true wave function and this is the true ground state energy. So this is your true ground state energy. And this is the true wave function. But of course, we don't know these. So what we are going to do is, we are going to pick a wave function psi. So you can note the difference between this psi and this psi. Here there are no whatever, this is capital psi and this is little one. And the energy is, let's say, E q star, right? So this is my trial wave function, and using this trial wave function, the energy that I will compute, that will give me an upper bound on the true ground state energy, right? That's the essence of the variational principle. So how will I compute E star q? So computation of E star q involves computing this quantity, if you like, let's say psi h psi over psi the inner product, and this will give me an upper bound on the true ground state energy, right? Now, this difference the difference between the energy that you have obtained by your trial wave function and the true ground state energy, this will always be more than true ground state energy, right? This difference, your aim is to minimize this difference, right? Now, how will you minimize this difference? You will minimize this difference by choosing your psi q as close to the true wave function as possible. The closer you are, the better it is, right? So, as psi q tends to psi q, I mean, this is trivial, you know this, E star q tends to EQ. So basically, the success of this method depends very crucially on how you choose, how you construct your trial wave function. If you're clever, if you do it cleverly, you might come very close to the true ground state energy. But if your choice is not good, then you might be very far away, right? So how should we choose psi q? Now the choice of psi q is dictated by the physical picture, the physics, right? I mean, you want to choose your wave function such that it obeys the physics of your system, or it conforms to the physical reality. Now, what's the physical reality here? The physical reality is that I will choose my psi such that it satisfies, number one, the condition that if I am too close to any of these ionic cores, then my psi should converge to the atomic orbital of that site, right? That's the point. That's what you did in hydrogen molecule ion also, hydrogen molecule problem also. When the electron is too close to the left hydrogen, then it is like 1s orbital of hydrogen atom, right? So that is condition number one. So condition number one is that your psi should collapse. I mean, collapse is the word that I chose, but if you have a better word, use it. Collapses to the atomic wave function phi n when the electron happens to be in the vicinity or in the close proximity of the nth site. That's point one. And second point is that since you're constructing a wave function for an electron in a periodic lattice, therefore you would demand that this wave function should be a Bloch wave function. It should satisfy the Bloch's theorem, because after all you're constructing a wave function for an electron which is living in a periodic lattice, right. So, second demand that you pose is that psi should be a Bloch function, should satisfy the Bloch's theorem, or people put it variously. Some say that this electron is a Bloch electron. It's not a free electron anymore, right? The free electron is exponential ikr, and the Bloch electron is exponential ikr modulated by a plane wave, modulated by a periodic function. So, that is a Bloch electron. So, satisfy Bloch's theorem. Which means that psi of whatever, I mean, you know what that means. Yeah. Wherever, whenever it is closest to the, n can be anything actually. So, wherever it is. That's a good point. That's a good point, and in fact, I did it, but I have also on the board v of x, and whatever we are doing here, this h is with this v of x, not with v prime x. I mean, I have drawn v prime x because I will use it at some point, at some later point. Right now, in your Hamiltonian, in this Hamiltonian is still minus h bar square by 2m del 2 del x square plus vx. I mean, we just wrote vx as little vx plus v prime x, because later on we will be using that. Sorry, I should have mentioned that, but you are right. So, this is it. Now, so let us construct our psi. So, we can write then psi of q as, of course, there is a x here, is equal to summation over n Cn phi n x minus Na. What is it? It's a linear combination of atomic orbitals, isn't it so? It's just C1 phi 1, C2 phi 2, C3 phi 3. This is a linear combination of atomic orbitals. That's how I constructed my wave function. This is what you did in hydrogen molecule problem also. Your trial wave function is just a linear combination of atomic orbitals, because then and only then it can satisfy the condition 1, otherwise it won't, right. So, it's a linear combination, okay, there is a better name for it, LCAO. Have you come across this LCAO? Very good. So, this is just an LCAO, and therefore, that is why this problem relates so closely to the problem of hydrogen molecule. But it is different from hydrogen molecule in the sense of this. This makes it different from the hydrogen molecule, where it's just not just LCAO. It has to be LCAO plus, now this will make condition 1 fulfilled. But what will make condition, does it satisfy condition 2 also? You have to choose your Cn in such a way that it does. Because phi is periodic, but what about Cn? So, what I mean, my assertion is that if you choose your Cn to be e to the power I q NA, then everything will be fine for you. My assertion is that if you choose your Cn to be this, then even the second condition will be fulfilled. It will become a block wave function. Otherwise not. So I choose C to be this, Cn to be this. So I pick the coefficients of my LCAO as this. And when I do that, then my wave function becomes compatible even with the second condition. You can let's check that. So then psi qx is equal to summation over n summation over n phi n x minus na exponential I q n a. Would you like to test whether it's a block function or not? The test is simply this, that it should have the periodicity, psi of q plus g should be equal to psi of q. Isn't it? We just proved it. Or you can try proving that mod psi square at x plus r is equal to mod psi. So do you see that? Do you see this? If you replace q by q plus g, what will you get? You will get e to the power iqna plus e to the power igna. And what is e to the power igna? It is e to the power igr, because na is r. E to the power igr is what? 1 exponential minus height. So therefore it is a block function. So we have solved half the problem. Sorry. No, we have not solved half the problem. We have basically arrived at some good position. We have constructed our trial wave function. It has passed both the tests. That much we have done. Now comes the harder part. The harder part is to evaluate the numerator and the denominator. Once we have done that, then we have the answer, we have the energy, right? So let's do that together. And this is a bit tedious part, and you might also find it a bit boring because there are details, but it's done very nicely in these notes, and I have already sent you these notes. So if you miss something, don't worry. You can go home, look at the notes, and I'm not going to basically use any fancy ideas, very simple ideas which you are very well familiar with. Orthogonality of wave functions on two different sides and so on and so forth. Nothing fancy. So let's evaluate the denominator first, because that's easier. So the denominator is psi, and that's integral psi star q psi q dx. X is going from minus infinity to plus infinity, right? Now plug in psi q, you have it over here. So this will become summation over n comma m exponential I q n minus m times a integral minus infinity to plus infinity phi star m phi n dx. This is okay with everyone? I have used an index n for for this, n for this and m for this. That's all I have done. Right? I had to use two different indices. Now, what do you think about this integral? Look, when m is equal to n, then this integral is 1. That's the normalization of the wave atomic orbital. And when n is not equal to m, so you have atomic orbitals at two different sites, right? Then this will be 0 because they overlap, because they are orthonormal or whatever the way you put it. So this is equal to 0 if n is not equal to m, and this is equal to, this integral is equal to 1 and n is equal to m, so this will become 1. So you are summing over n sides just, so this will become n. So this is your denominator if m is equal to n. So the denominator is done. Now let's go to the numerator. Is it fine? Do you have any questions here? You agree with everything on the board? Good. Very nice kids. I had problems actually, but but it's written in the notes. You can go home, you read it up. Okay, so denominator was rather straightforward. Now in the numerator there is a little bit of trick. So let's come to that. So the numerator is nothing but summation. Let's create some more space. Numerator is summation n comma m and exponential I q n minus m, and then integral minus infinity to plus infinity phi m star h phi n dx. Is this fine? Everyone is good? Summation is correct? Correct. Thanks a lot. These little mistakes, sometimes they cost a lot towards the end. Correct. So this is what the numerator is. So far it looks pretty simple. Now here is where the role of this is going to come. So what I am going to do now is this integral in this h, I am going to write this h as, so minus infinity to plus infinity phi star m, and I will write this h as h naught plus v prime. You are with me? H naught is with little v. We can break it into two integrals. So the first integral will be correct. Now this piece over here, who will tell me what is this? Louder. This is the energy of the atomic orbital, isn't it, when the atom was in vacuum, right? Right? Everyone is okay? So, this is nothing but E naught. Remember, this E naught is the energy of the atomic orbital. What about the second integral? Okay, so the first integral is E naught if n m, and this is equal to 0 if n is not equal to m. Why? Because once again you will get E naught times, so when this operator will act on this, you will get E naught phi n, E naught will come out of the integration sign and you will get integral minus infinity to plus infinity phi n, and phi n we just showed phi n is 0, right? Now what about the second integration? The second integral over here, so we have this term also, you remember that. So this summation exponential I q n a, q n minus m a, and this summation with a block, this block, and this summation, this block, where this block is this. And once again, when n is equal to m, you will sum this over n sides. So this will be then so this will be n times E naught, right? Right, because you are summing it n times, right? And the second integral is the one which is a little bit tricky. So let's rewrite it here. So the second piece in our integration. So this is the first piece, and here's the second piece. So let's see how to calculate the second piece. So the second piece is summation and m I q n minus m times a integral phi star m v phi n dx. Now the first point is that if you assume, and this assumption is fairly good, let me first make the assumption and then I will discuss it. If you assume that only the nearest neighbors interact, what that means is what is written here, that the orbitals on 0 can overlap with the orbital on the site -1 and the site -2. But the extent of this orbital, even in the condensed phase, in the crystalline phase, is not so much that the orbital on the site 0 will start overlapping with the orbitals on the site 2, because they are still too far apart, right? So this basically what you will see towards the end of this lecture is that the electron, which was fairly localized when the atoms were very far apart, when you bring them together, then the orbitals will overlap, and because of that the electron will be able to hop from one side to another side. So this hopping is made possible because the orbitals on the adjacent sides, they overlap, right? So if you go to the next nearest neighbors, this will not work out. So what that means is that if m happens to be let's say n plus minus 2, all right, phi star n plus minus 2, this is v prime by the way, v prime phi n dx, then this quantity will be 0. There is hardly any overlap. So this is 0. This quantity is 0. Does this make sense to you? Right? This quantity is 0. And this is, but not, so the only non-zero term in this case would be when n is either plus 1 or minus 1. Taking n to be 0, then m can be plus 1 or minus 1, right? So what kind of terms you will have? You can take n to be 0 and m to be plus minus 1. So that will give you one term of this integration. Then you can take n to be 1 and then your m will be 1, 0 and 2. Then you do n to 2 and you get m equal to 1 comma 3 and so on and so forth. And similarly on this side. So basically this integration, this second piece has these kind of terms. Is this point clear to you or not? Is this point, does it make sense? Does it make sense? So you will have, for instance, when I put n equal to 0, you will get phi 1 v prime phi 0, phi minus 1 v prime phi 0, and of course phi 0 v prime phi 0. These are the three terms that you will get. Then you will put n equal to 1 and then do it and so on and so forth. This is how you have to proceed, right? So therefore you have does for given n we have only 3 non-zero terms. And what are these? These are phi n plus 1, v prime phi n, and then phi n v prime phi n, and then phi n minus 1 v prime phi n. इसको प्लस कर लो, इसको माइनस कर लो. These are the only 3 terms that are non-vanishing if you fix the n. So what you do is you evaluate this sum, the sum of these 3 terms, and then run this summation over all sides. Got it? So you are summing it as these 3 triplets. So this triplet for the nth side, then the next triplet for the n plus 1th side, the next triplet from n plus 2th side, and so on and so forth. This is what you have to do. Got it? Got the point? Right. The rest of it is just calculation. So therefore, I can write the second piece of my integration as summation over n exponential I. If you don't like me writing n here, you may object. No, why would you object to it? You won't. If you will, then I will change it. And then inside this, you have e to the power I q a integral phi star n plus 1 v prime phi n dx plus integral phi star n v prime phi star phi dx phi n plus exponential minus iqa integral phi n minus 1 star v prime phi n dx. Sorry? In the beginning. In the beginning, we should not have that. No. We should have. From here we have to do. Correct. 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 Then we don't have this. Then we have just the summation over n. Then this is a mistake in my notes. Right? And for the nth site, we have these three terms. And then we run this sum over all the sites. From every site, we will get these three terms. Now, so because of the symmetry of the problem, if you work this out, for any triplet, then the next triplet will give you the same contribution. The magnitude of the contribution from this triplet or this triplet is going to be same, because this is demanded by the lattice symmetry, translational symmetry. So if this is coming out to be, let's say, some quantity x, then this will also come out to be x. This triplet will also give you x. So it will be, and since you are summing it over all the sites, it will be the total number of site times x, and total number of sites are capital N. So therefore, this summation can actually be dropped, and we can simply write here a capital N, right? So therefore, this is just capital N, right? Now let's look at these integrations, these three integrations. So also, one more thing, one more simplification, which is that this integration, the value of this integration is same as the value of this integration. This is the same quantity evaluated between the pair n plus 1 and n is the same quantity evaluated between the pair n minus 1 and n, right? On the left hand side as well as on the right hand side. So left right symmetry. So these two integrations are also equal. Now if I call this integration as gamma, then that means this integration is also gamma, right? And I call this integration, which is the integration on the same side, n, as beta. Okay? Then what have I achieved? What I have achieved is that this is nothing but gamma with e to the power iqa, gamma with e to the power minus iqa. You take gamma out, and then you have e to the power iqa plus e to the power minus iqa, that you can write as 2 cos qa, right? So therefore, this will become also one more point. So let's write it formally, because this is important. So let's write it formally. So what we do is we take gamma is equal to minus phi n plus 1 v prime phi n dx, which is equal to integral phi n minus 1 v prime phi n dx. This is gamma. Gamma is negative of this. You can say minus gamma is equal to these two integrals. This is how it is defined. Now, the second integral is defined as minus beta. So, minus beta is just phi n v prime phi n dx. That's my second integration. So, we are now ready with the expression. So, we got the you remember that the first this had two pieces. The first piece is n times E naught. You remember that, right? So therefore, I am now ready to write the energy EQ star finally. So EQ star is equal to 1 by the denominator, and we evaluated the denominator right in the beginning, and the value of the denominator was n, capital N, right? Capital N. Then we write here the numerator. So in the numerator, the first piece is this. Its value is n times E naught minus the second piece, and the second piece is n times twice of cos qa beta plus beta, right? So it will be minus beta minus 2 gamma cos qa. Right? And of course, this is also with n. Right? This also has n in front. So n will come out common, in fact, from all the terms. So n gets cancelled. So what we get then is E star q is equal to E naught minus should be plus minus beta minus 2 gamma cos q of A. That is the final expression for the energy. Well, the maths is all done. We don't have to do any more maths. We just need to talk 5 minutes, 5 minutes maybe, but later we can discuss over the computer on the online session. So I need to just discuss it now. So beta, which we have obtained, this quantity beta, what is this actually? This is simply the amount by which the energy level will lower itself from its value in the isolated atom due to electronic attraction felt by the electron from the n minus 1 nuclei. This is what this term is. So there is an energy lowering. So this is the energy of the isolated atom, the energy of the electron in the isolated atom. Then you lowered it by an amount beta. This lowering is coming because of the nuclear charge seen by the electron at the nth site by the remaining nuclei, right? So this is what this quantity is. And this, then there is further lowering by an amount gamma, minus 2 gamma cos qa. And this is actually, this term makes it possible for the electron to hop from site to site. So this allows this possibility of going from n plus 1 to n, or from n to n minus 1, or vice versa. Right? So this is the hopping term. It allows hopping of the electron. And this is just This is just the electrostatic lowering of the energy, the positive charge of the other and -1 nuclei which are around this electron. Because of that, the energy is lower. So the energy lowers because of two reasons. One is the pure electrostatic effect, and second is the effect of hopping. Okay, and then you can plot here a very nice plot, which is this is 1 by spacing, atomic spacing. So here the atomic spacing is A, right? So this is 1 by A basically on the x-axis, and on the y-axis is energy. Now when you are here, this is isolated atoms. When the atoms are isolated, the energy is E naught, right? Now when you bring the atoms closer, which means you're going this side, the energy starts lowering. The energy starts lowering primarily because of the beta term. Okay, so the energy lowers. Okay, and this lowering is the lowering by an amount beta, and simultaneously you also have some spreading of this. So as you go this way, it gets more and more spread out. This spreading this quantity is gamma. So this is 4 gamma. 4 why 4? Because 2 gamma and 2 gamma, that will give you 4 gamma. So this is what it looks like. And let's say if this is the if this is actually R naught, or which is equal to A naught, A in this case, okay, then this is how it looks like. Okay, and you can also plot E versus Q from here, E versus Q. So when Q is plus pi by A, this has a, so when Q is pi by A, what will be this? What will be this? This number is cos pi. Cos pi is minus 1, I believe. So this will be E naught minus beta plus 2 gamma. And when Q is 0, then this quantity is what? The cos 0 is 1. Then it is E naught minus beta minus 2 gamma. So here the energy is E naught minus beta minus 2 gamma, and that is why the spread of the band is 4 gamma, which is the difference between the maxima and the minima. And if you plot, this is simply a plot of cosine function, so it's going to look like this. So this is your band that you got. The bandwidth is 4 gamma, and these are your various Q values. And it can, if you have exactly n electrons, then it will be half filled. That means all these states are filled here, and the Fermi level will lie here, and it will be a metal. And if it is 2 electrons per site or per unit cell, then all these sites will be filled, and it will be an insulator, right? Of course, here we got only one band. Why? Because we started with only one orbital. At each atom, we had only one orbital. If you take 2 orbitals, then the same phenomenology works for 2 orbitals, so you will get 2 bands, right?